The salt bridge usually consists of a strong electrolyte, which is made up of ions, for example, silver nitrate, potassium chloride, etc. Strong electrolytes. Salt bridge prevents the diffusion or mechanical flow of solutions from one half cell to another. So suppose we have to use different solutions in different half cells. So we can't just mix these because otherwise there will be no surface boundary. If we mix these two solutions, there will not be any surface boundary. So we have to have a mechanism which can prevent the diffusion, at the same time can allow the flow of current also. It prevents or minimizes the liquid-liquid junction potential. This is slightly, you have to imagine what I am talking about. If two liquids, say this is just imaginary condition I am talking about, say this is one liquid and there is another liquid. These two liquids, suppose there is imaginary boundary. This is imaginary boundary between two liquids. So even if there is imaginary boundary, there will be some potential between these two because these will neutralize. So there will be transfer of ions here also. These will neutralize unnecessarily even if there is no connection, no current flowing. So even if there is no current flowing, the ions will neutralize. Okay. So there will be a potential difference between these two. So it prevents that potential difference. So salt bridge prevents the diffusion and it prevents the liquid-liquid junction potential also. Salt bridge acts as an electrical contact between two half cells. It provides electrical contact means the flow of current between two half cells. These 3 points directly, indirectly important from JEE and NEET perspective. However, these might be asked in CBSE as well. So it is good to know the function of salt bridge. Now, if I understand the functionality of salt bridge, this is how it works. I am talking about the Daniel cell. You have anode where oxidation takes place and cathode where reduction takes place. Copper is reduced to copper metal. And the salt bridge is potassium nitrate. I am explaining how the current flows. Electrons which are generated at anode, these are the electrons. These electrons travel through wire to the cathode. Okay. So it means current is flowing in this direction. Current direction is opposite to flow of electrons. Circuit has to be completed. To complete the circuit, if current is in this direction, it means here current should be in this direction. Direction of current inside cell. Okay. It means positive ions will move in the direction of current. Current is termed as positive movement, movement of positive charge, opposite to the movement of negatively charged electrons. So if positive charge will move in this direction, means negative ions will move in opposite direction. Anion in reverse direction to cations. So how this happens? This happens because at anode there is a tendency that zinc will get oxidized to Zn2 plus. This Zn2 plus has to be neutralized by anion. So that's why anionic part of this salt bridge moves to the anodic part, anode half cell. So that Zn2 plus and 2NO3 minus combine and they produce zinc nitrate. Okay. Similarly, potassium will move to this direction. Here Cu2 plus is getting reduced to Cu. Suppose this is copper sulfate solution. So if this is copper sulfate solution, it will get reduced to Cu2 plus SO4 2 minus. Cu2 plus got reduced to copper, but these SO4 2 minus must be neutralized. So for these, you get 2K plus SO4 2 minus, you get K2SO4. So neutralized in the cathode half cell as well. It means after some time, the cell will get exhausted. And that's why these cells get exhausted, because all the salt ions in the salt bridge are used up. So electrolytic cells get exhausted when all the ions in the salt bridge are used. Yes, they will. Anode will have negative potential, cathode will have positive potential. So if it is asked, this is the diagram you need to explain. Similarly, the salt bridge can have different ions. The concept will be same. Means the positive ions will be neutralized by anion, and here negative ions will be neutralized by cation. So there exists two voltages. The one is between the electrodes, that is metallic bars, and the other is between the liquids, between the charged liquids. The voltage between the metal bar or electrode is positive. The voltage between the charged solution is negative. This is what you need to remember. That's the convention, basically, what we consider, which one we consider as positive and negative. Based on that convention, if you see the diagram here, this is considered as positive because this one is plus, this one is minus. Here. So current is flowing in this direction from positive to negative. So this potential is considered as positive. Inside, the current is flowing in this direction from anode to cathode cell. So that's why negative, opposite. Outside here, opposite to ether. This is something I have explained, that NO3 and K plus get neutralized. Now the question, how would you determine the standard electrode potential of the system Mg2 plus Mg? How will you determine? This is something we talked about in previous class. Anyone? What is the method to determine or to compare? I am giving you a hint. Ashi, yes, correct. So we will compare it with hydrogen half cell. We will compare it with hydrogen half cell to get its potential. The potential is always with respect to hydrogen half cell, the standard hydrogen electrode. So that's what we will do. The standard electrode potential of Mg2 plus Mg can be measured with respect to the standard hydrogen electrode represented by platinum hydrogen ion. And remember, when we represent the standard, A standard means the concentration is unity. So in case of gas, the concentration is 1 atm. In case of ions, aqueous ions, the concentration is 1 m. Molarity is 1, pressure is 1 atm. A cell consisting of MgMgSO4 aqueous 1m as the anode and standard hydrogen electrode as the cathode is set up in this case. So Mg2 plus Mg is actually represented by this one. The important point what I mentioned in the previous class as well, when you represent the cell, in cell it will be oxidation reduction part. You will always write oxidation first and reduction next. But if it is asked the redox couple, then both will be in reduction form. Although in that case also oxidation will be written as first. But in cell representation, and this is what will be asked most of the times. So you need to be clear. This is the way you will be using most of the times. Oxidation, because here increasing the oxidation state from 0 to 2 oxidation. Here reduction plus 1 to 0 reduction. Then the EMF of this cell is measured, and this measured EMF is the standard electrode potential of the magnesium electrode. Why? Because it is with respect to hydrogen half cell, and hydrogen half cell potential is considered as zero reference. So we will write E naught means standard EMF of the cell will be E cathode minus E anode. Okay. Here ER for the standard hydrogen electrode is 0. So we will write 0 minus EL, that is minus EL will be the electrode potential here. Remember what I am talking about. Here oxidation is taking place. So this one will be anode. Anode will be Mg2, Mg2 plus. This will be anode. This will be hydrogen cathode. Because here reduction is taking place. Okay. So E cathode is written as E right. E anode is written as E left. E naught will be E right minus E left. E right is 0. Means it will be minus EL naught. Next question. Can you store copper sulfate solution in a zinc container? Okay, Mehak. The reason also? She okay, correct. Shivani, yes, correct reason. Mehak, correct reason. Okay, zinc is more reactive than copper. So zinc will replace copper from its copper sulfate solution. One Ahan, yes, good. Copper sulfate solution cannot be stored in zinc container. Next, consult the table of standard electrode potentials and suggest 3 substances that can oxidize ferrous ion under suitable conditions. So in these type of questions, basically electrode potentials will be given. This question I have taken from NCRT. In NCRT, it is written that you can consult the table given. The question is, now my question is something different, which you can answer. The question is, you need to write three substances that can oxidize ferrous iron. My question is, in the table, reactivity table, which is given in the notes, in the books, and I hope you have gone through. Suppose this is the ferrous iron, and oxidation of ferrous iron means it will be converted to Fe3 plus. So these three substances will be at the above or below. Above or below. You need to just write these substances will be above or below. I am looking for only above or below. Ashki correct, Mehak correct. Shashwat correct, Shivangi correct. Others, I'm looking for answers. Rita correct. Okay. So I in the previous class also I asked you when during end of the class that whether the fluorine will be at the top or lithium will be at the top. We said that fluorine will be at the top because it is the highest or best oxidizing agent. Yeah. So these will be at the top or above this one, which can oxidize. So at the top, we have better oxidizing agents. At the bottom of that table, we have better reducing agent. If the question is better reducing agent, it will be below that one, whatever we are talking about. Better oxidizing above that one. Yes, lithium will be at the bottom. Yes, correct. Yes, Ahan. If we talk about specifically, yes, correct. Last equation. Last equation, this N is there, okay, which is not pronounced. Let's give an equation. Because till now, what we have done, till now we have considered the standard electrode potentials only, means the concentration or the pressure is one unity, 1 atm or 1 m. But it might not be the case always. The cells can have the different concentrations and it will change when we use the cell. The concentrations will change of the solution. So if that is the case, and that is actually the case, what should be the equation? The equation in that case is given by this. So if I'm considering this is the reduction half cell, remember I'm considering only half cell at the moment. I will combine, I will use the same formula, E cathode minus E anode to get the combined whole cell potential. But for half cell, NERNST said that the reduction potential of the cell will be given by its standard reduction potential. So this is electrode potential. This is standard electrode potential. Who will tell me what is the difference in electrode potential and standard electrode potential? I have just told what is the difference between these two. Okay, Shivangi, yes. Shashwat, yes, good. Ashi, that is the result. But how will you define standard electrode potential? When we say standard electrode potential means we are talking about, yes, you are correct when no current is passing through it, that okay. But also when there is no change in concentration, initial concentration at 1 bar pressure, 1 M. Okay. So standard electrode potentials are when we are talking about the ideal case. And these potentials are constant. We know these. So these have already been calculated. So the table is there which gives you the standard electrode potential because these will not change. This will be constant of a particular cell for a particular cell. Yes. So NERST said that if you want to calculate electrode potential for any concentration, not just 1M, then we will use the standard electrode potential and then minus RT by NF ln M by Mn plus product concentration divided by reactant concentration. This ln can be converted to log by multiplying it by 2.303 log M divided by Mn. RT, these have their specific meaning, gas constant, T is temperature in Kelvin, F is Faraday constant. Faraday constant is the charge on 1 mole of electrons. What is this F? This F is Faraday's constant. And what is this? This is charge on 1 mole of electrons. And what will be the charge on 1 mole of electron? It will be 1 mole charge on 1 electron into 1 mole. Now I have approximated. 1.6 is approximation. It is more than this. 6.022 is approximation. It is actually more than this. So when you multiply these two, you will not get what I'm going to write. Okay, this is approximately 96500 or 497 exactly. But we will be using in calculations 96500 coulombs. This is the Faraday's constant. N is very important to know. What is N? N is the number of electrons exchanged in the balanced reaction. To understand this, when we talked about the Daniel cell, we said zinc plus Cu2 plus gives us zinc 2 plus plus C. The total number of electrons in this case was 2 because in balanced reaction it was zinc ion plus 2 electrons and copper ions gained these 2 electrons to get reduced to copper metal. So N will be 2 in this case because 2 electrons got transferred from one cell, one half cell to another half cell. Okay. From this anode to cathode half cell, 2 electrons got transferred and 2 in balanced reaction. So try to memorize this reaction, okay? This formula equation basically. Now you remember from your 11th grade in equilibrium that concentration of solids is considered as unity. So this concentration of solid will be considered as 1, and we will write it 1 divided by concentration of metal ions. M here stands for metal. Don't think it is Mn. It is not Mn. It is Mn plus, means N is charge. As I said that we have a table where all these values are already calculated. These are already defined. R is gas constant, F is Faraday's constant, specifically 487, but 500 we say. T is temperature in Kelvin. Mn plus is the concentration of species, Mn plus ion. N is the number of electrons transferred in the balanced reaction. But remember, this is only one half cell. Similar reaction will be there in another half cell. So this one I have written for reduction half cell. Here reduction is taking place from some plus n oxidation state to zero oxidation state. Reduction is taking place. I have written for reduction. Reduction happens at cathode. Means whatever you are calculating here is something related to cathode. Similarly, there will be reaction for anode also. But before that, just a recap of the table we had talked about. At the top, we have chlorine, means it is best oxidizing agent. And then we go downward and lithium is best reducing. Means the most negative electrode potential will be best reducing agent. The most positive electrode potential best oxidizing agent. So a negative E naught means that redox couple is stronger reducing agent. For example, for lithium, it is most negative. A positive electrode potential means redox couple is a strong oxidizing agent or weaker reducing agent. Then hydrogen couple. Hydrogen couple has been assigned 0. Electrode potential 0. So if it is negative means the redox couple is better reducing agent than hydrogen couple. If electrode potential is positive means it is better oxidizing couple than hydrogen couple. So in Daniel cell, the electrode potential for any given concentration, okay, not unity, just this will be the reaction, because at anode the reaction will be this one plus 2 electrons. At cathode the reaction will be this will gain 2 electrons, copper. Okay. So here concentration of copper has been considered as 1 divided by concentration of CO2 plus, which is written as it is. Similarly, at anode, we will write the similar reaction. E zinc 2 plus to zinc standard minus RT by 2F because N is 2 here, Ln. Now here, one important point, okay? One important point. Whether we talk about this one or whether we talk about this one, as I said in previous class also, these are always reduction potentials. These are reduction potentials. And this is where common mistake occurs. Now, if these are reduction potentials, although this is oxidation which will be taking place at anode, I will write the reaction as reduction. For this equation perspective only. For this equation perspective. So here it will be concentration of zinc divided by concentration of zinc ions reactant. Same concept as you have used in equilibrium to calculate the equilibrium constant. But solid concentration is considered as unity again. So I got the reduction potentials for both half cells for cathode and anode. And now you know the formula, how to get the reduction potential. For that, you will do the reduction potential of the cell will be E cathode minus E anode. All both of these are reduction potentials. If you consider this as oxidation potential, as I said in previous class, then it will be plus. Okay, so don't go into those complexities unless the question talks about that. And we will be doing those type of questions also so that you can understand what I am talking about. Here both are reduction potentials. Substitute the values. So when you substitute the values, this minus this will actually give you the standard electrode potential of the cell because it is E cathode minus E anode for standard reduction potentials. These are just reduction potentials. Here, these are reduction, standard reduction potentials. So this will be E cell naught. This is E cell reduction potential, E cathode minus E anode, E cell. Standard reduction potential, E cathode minus E anode, standard EMF. This is missing. Now it is correct. This was already negative. This was positive. When you have taken minus common, it will become negative. Now, when you simplify this, you will get this one. Okay? Because you know that log A minus log B is log A divided by B. So similarly, ln A minus ln B will be ln A divided by B. So this is the main equation you have to remember. Okay? And this is the NERNST equation. This is the NERNST equation, which will actually change depending on which cell we are talking about. Only this part will remain same for all cells, only this part in this equation. N will change and these concentrations, these ions will also change depending on which cell you are talking about. Okay? But this is called NERNST equation. Now we have fixed values of R, T, and F. R is gas constant, T is temperature in Kelvin, F is Faraday's constant. So when we simplify this, we get 0.0591, 0.0591, which is written as 0.059. In few cases, 0.0591 also. So you can use this value directly. You don't need to write the formula in terms of RT by F. You can use this formula directly. You just need to write N here and substitute the value of N with the number of electrons exchanged in the balanced reaction. Okay. So for a general electrochemical reaction where you have N electrons transferred, A plus B plus gives you C plus D, it will be like E cell equals to E cell naught minus RTNF ln products concentration raised to their stoichiometric coefficients divided by reactants concentration raised to their stoichiometric coefficients. Means Q, C at any point of time. Which QC is same thing as you have done in equilibrium chapter. Now the question. Represent the cell in which the following reaction takes place. So first you have to represent the cell. And when it is represent the cell, it is something oxidation reduction form. Then calculate the E cell if E cell naught is given. So first when you represent the cell, you will say oxidation part. Oxidation part is Mg to Mg2 plus, and then salt bridge. Basically, this is representation of salt bridge. Then reduction part. Reduction part is Ag plus to Ag. Now, sometimes these concentrations are also mentioned when you are presented. So the better way is oxidation salt bridge reduction for representation. This is representation. Oxidation is magnesium 2 plus, because here oxidation state is 0, here oxidation state is plus 2. It means it is oxidation. So write that part, Mg solid to Mg2 plus, and write its concentration 0.130 m. Then you have salt bridge and reduction part. If you see Ag plus, here you have plus 1 oxidation state, here you have 0 oxidation state, means it is reduction in oxidation state. So it is reduction part. So write it Ag plus, mention its concentration 0.001 m, and then Ag solid. So with concentrations, you can mention the or represent the cell. This is the way to represent the cell: oxidation part, reduction part. Now the calculation of E cell. Write the NERNST equation. So NERNST equation you will write here using NERNST equation. E cell will be E cell naught minus 0.0591 divided by n log. Now remember one point. When I mentioned 0.0591, it is log, not ln. Means I have converted ln to 2.303 log. So this 2.303 also included in 0.059 here. So log concentration of Mg2 plus divided by concentration of Ag plus whole square. Why whole square? Because I have 2 here. Because it is QC. Concentration of solids will be considered as 1, so that's why not included. Now substitute the values. 3.17 minus 0.0591 divided by 2, because 2 electrons will be used, whether you convert Mg to Mg2 plus or 2 Ag to Ag, it will be 2. Log concentration of Mg2 plus 0.130 divided by concentration of Ag plus whole square. Obviously, the values of the logs will be given. In board examination, all log anti-log values will be given in the question. When you solve, you will get answer as 2.96 volt. Method should be clear. If there is any confusion, let me know. Any concept is not clear, let me know. Yes, Ashi, your NERNST equation and substituted values correct. Next topic, equilibrium constant from NERNST equation. So basically it is the same thing, but now we will consider that there is equilibrium achieved within the cell. So if equilibrium has been achieved, the same equation will be for equilibrium constant. We will call this as Kc instead of Qc. Now we will call it Kc. So we will write it as Kc. We will get the answer. Most important point, in this case, E cell will be zero because at equilibrium, there will be no current flowing. E cell will be zero. E cell naught has a fixed value. So E cell naught can never be zero. Always fixed value. E cell will be zero at equilibrium. So in the NERNST equation, substitute the values and we get E cell naught equals to 0.0591 divided by 2 log AC. This is 0.0591. This V is just unit for the potential, nothing else. So you can write actually instead of writing here, you can write volts. Again, formula directly you can use if Kc is asked. Divya, it is the value of these all, as I said. So this is actually 2.303 into 8.314 into 298 divided by 96487. Everywhere, they've everywhere, whether it's this question or this is previous question, these are constants everywhere. So in general, yes, it is E cell not equals to 2.303 RT by NF, but this value you know is 0.0591. So you can directly use that without writing this. You can actually write the formula as like this. It is acceptable to write the formula like this. Otherwise, you first write this and then one more important point. Sometimes it is mentioned that temperature is something else, 300 Kelvin, etc. Then don't use this formula because this one is specifically when temperature is 298 Kelvin, 25 degrees Celsius only. If temperature is not 290, not 298 Kelvin or 25 degrees Celsius, then you must use this formula only. If temperature is not given, you will assume temperature as 298 Kelvin. Next question, calculate the equilibrium constant of the reaction. This one. So you will apply the formula E cell naught equals to, because temperature is not given, you will write 0.0591 divided by transfer of electrons, 2 electrons, okay, 2 into log Kc. E cell naught is given 0.46 equals to 0.0591 divided by 2 log Kc. In this case, anti-log will be given. You will get the answer. Okay. So you will get log Kc equals to something, say x. So Kc will be anti-log of x. Okay. Anti-log of x is nothing but 10 to the power x, remember. Antilog of x is 10 to the power x. So if this number is, say, uh, some integer 2, 3, 4, in that case, the antilog might not be given in the question because you are expected to know the antilog of at least the integers. So if suppose it comes out to be log kc equals to 3, then kc will be antilog of 3 means 10 to the power 3, that is 1000. Okay. Otherwise, this antilog value will be given in the question. Next, electrochemical cells and Gibbs energy of the reaction. Before I move further, mark your presence. Just write present in the chat box. Everyone, write present in the chat box. Don't respond to everyone, respond to me only. Okay. Now, electrochemical cell and Gibbs energy of the reaction. So now we will be talking about Gibbs energy delta G, Gibbs free energy. This is again just a formula you need to remember. Gibbs energy of the reaction is given by delta Rg equals to minus NFE cell. Write down this formula. We will be using it extensively. So E cell is an intensive parameter, but delta Rg is an extensive thermodynamic property, and the value depends on N. Who will tell me what is intensive property, what is extensive property? You can tell me on mic also, you can tell me on chat window also. If it is written intensive parameter, extensive parameter, what it actually means? Shashwat, yes, correct answer. Good. So intensive parameters are those parameters which do not depend on the amount or concentration. Yes, Archie. Matter, you can say, yes. RV, yes, you have written matter. Yes, that is correct. Amount, correct. Yes, one minute. So opposite is extensive property, which depends on the concentration or amount. E cell is intensive property means does not depend on amount. Okay. Yes, correct. This equation is very important. You need to memorize. The standard electrode potential for Daniel cell is 1.1 volt. Standard electrode potential is given. Calculate the standard Gibbs energy for this reaction. This is again the reaction which happens in Daniel cell. So for this one, you need to write delta G equals to minus NFE cell. Now, what is asked? A standard is asked. So if a standard is asked, these will be standard. A standard electrode potential is given, it will give you a standard Gibbs energy. So substitute here number of electrons transferred to F96487. E cell not 1.1. Multiply, you will get the answer. Okay. Remember here it is in kilojoules. you will get in joules. When you convert it in kilojoules, this will be the answer. And this is per mole. Why it is per mole? Because the Faraday is for 1 mole of electrons. Yeah. Yes, Shashwat, correct. But you need to include negative sign there, Shashwat. And okay. So just one important point here. When I say Gibbs energy is minus n F E cell naught, this F is Faraday's constant, which is the charge of 1 mole of electrons. Means this Gibbs energy you will get per mole for 1 mole. Next question. Calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. Question is easy. You just need to understand what is required, what is given, how will you get the required information from the given information. That is the only thing. Potential of hydrogen electrode in contact with a solution whose pH is 10. Just tell me the method. Don't tell me the answer. You can tell me the method. Yes. Okay, Ashi, correct. So for potential of hydrogen electrode, you need hydrogen ion concentration. And pH can give you hydrogen ion concentration. Right? Means log H plus is minus pH, means minus 10. Means H ion concentration is anti-log minus 10. And I told you that anti-log is nothing but 10 to the power that 10 to the power minus 10. So you got pH as 10 to the power minus 10 moles. Molarity, moles, not molarity, moles per meter. The moment you got that, now you can apply the hydrogen half cell. H plus gains 1 electron, gives you hydrogen. Apply the formula, NERNST equation, E cell equals to E cell naught minus 0.0591 divided by N log H2 divided by H. And you know that E cell naught for hydrogen cell is 0. So it will not be given to you. You need to know that reference point for hydrogen half cell standard electrode potential is 0. Okay. The standard electrode potential, this is 0. Hydrogen is considered as here 1 bar. The concentration here, because it happens at the normal pressure, and normal pressure is considered as 1 bar. But this concentration is different, so that's why we have taken as 10 to the power minus 10. Okay. 10 to the power minus 10 when goes into the numerator becomes 10 to the power 10, so it will be actually 10 to the power 10. That is 10 log 10, that is 10 into 1, 10. So this whole will be 10. When multiplied with 0.0591 will give you minus 0.591. So two important points here, rather three. The first one is that you need to understand you will get hydrogen ion concentration. You need hydrogen ion concentration. Then you need to understand and you need to remember the reaction which happens in hydrogen half cell. Basically, this is standard hydrogen electrode. E, standard hydrogen electrode reaction, which you need to remember. Then you need to know that E cell naught for standard hydrogen electrode is 0. Then you need to know that these reactions happen at 1 bar because it is a standard hydrogen electrode. That's why 1 bar it happens. But this concentration is changing because pH is given. The reaction is carried out at normal pressure. Normal pressure here is considered as 1 unity. These 3 points you need to know to answer these type of questions. Next question. Calculate the EMF of the cell in which the following reaction takes place. You need to calculate the EMF, means E cell. E cell naught is given. So write NERST equation. You will write using NERST equation. E cell will be E cell naught minus, temperature is not given, you can use 0.0591 divided by N log nickel ion concentration divided by silver ion concentration whole square. Substitute the value, N will be 2, plus total exchange of electrons is 2 in the balanced equation. So it will be 1.05 minus 0.0591 divided by 2 log nickel concentration 0.160, silver ion concentration 0.002 whole square, and you will get E cell. When you solve this, you will get the answer in volts. Okay. So solve it and get the answer. Next question. The cell in which the following reaction occurs has E cell naught as 0.236 volts at 298K. It is 298K, you can use 0.0591. Calculate the standard Gibbs energy and the equilibrium constant of the cell reaction. Standard Gibbs energy standard will be delta R G naught equals to minus NF E cell naught. E cell naught is given. F you know 96487. For calculation, you can use 96500. Instead of 96487, this is accurate. For calculations, you can use this one also. It will be minus number of electrons transferred. Number of electrons transferred in this case, who will tell me? What will be the value of N? No, Shivang, no, Shivangi, Shashwat, correct. Divya, no. The value of N. Ashi, no. Arohi, correct. In balanced equation, if you write the reduction, it is 2Fe3 plus gives you 2Fe2 plus. So here total charge 3 into 2 plus 6, here total charge plus 4. It means it will get 2 electrons. So that 6 minus 2 will give you 4. Okay. So two electrons, similarly, two electrons transferred in oxidation half also, minus one, zero. But there are two iodines. It will be two electrons. These two iodines, iodide, when give you I2, will have two electrons here. So here minus two charge, here minus two charge total. Here total plus four, total plus four. Charges must be same on both the sides. So you will balance the charges using the electrons. So you need to have two electrons. So N will be two. So you will say delta G naught equals to minus NF E cell naught, that is minus 2 into 96487 into E cell naught is 0.236. Okay. This will be actually in joules. You will convert it to kilojoules. Once you have this, okay, then you have to calculate the equilibrium constant. For equilibrium constant, you know E cell naught equals to 0.0591 by N log Kc. Here I'm using directly 0.0591 because temperature is 298 Kelvin. Otherwise, I would have used RT by NF. Substitute the values and get the value of Kc, equilibrium constant.